Okay, in this section, 7.10, Entropy and the Second Law of Thermodynamics, I'm just going to highlight a few main points of the second law of thermodynamics, and then we'll do one example. So first of all, let's consider a few physical processes. For example, we can consider mixing a red liquid and a blue liquid to make kind of a purple colored liquid, or melting ice, or heat moving from a hotter to a colder area. All of these processes are irreversible. If you can picture filming these processes, filming the liquids mixing, and then playing the video in reverse, in rewind, what you would see is a process that never physically happens. And you can look up more formal definitions of that, but that's a good way to conceptualize what an irreversible process is. Okay, so let's consider a simple irreversible process of just maybe a gas. We can mix two gases, one hot gas and one cold gas, and when we mix them, we end up with a gas at a temperature in the middle at thermal equilibrium. So that process on its own is irreversible. But if we consider one of the interactions on its own, just two gas molecules colliding and mixing, that process could be reversible. So we can imagine those two particles moving apart, and then we could reverse that process essentially. And many interactions that we are considering in thermodynamics are macroscopic interactions that are made up of many microscopic interactions. So many small processes like this one collision between molecules. And so far we've seen nothing in the first law of thermodynamics. Just remember that the first law was that the change in thermal energy is the heat transfer and the work done on the system. Nothing in that says that this isn't possible. So let's look into the second law and why this doesn't occur. Okay, so let's first consider two containers. And in each one, this one will have N1 and this has N2. And there's a number of balls in each container. So maybe there's 8 in this container and maybe 1 or 2 in that container. So I have 2 containers here, and from each container I'm going to randomly pick a ball out of all these containers, and the ball that gets chosen moves into the other container. And you can see that with more balls in this container, it's more probable that I'll be choosing a ball from N1 and moving it into N2. It's not impossible that I'll take a ball from N2 to N1, though. That interaction is still possible, and it still will occur. But now let's assume that I have 100 balls in this first container. Then I'm going to randomly choose a ball out of these 102 balls and then choose one and move it to the other container. And now it's very improbable that I would select these two and move them to the other container. So mostly I'm going to be moving balls from N2 into N1, eventually so that we end up with the same number in both containers. That would be the thermal equilibrium, ending up with the same number in each container. So you can imagine this as energy. So this would be the hot substance with all of the energy, and we're moving energy into the colder substance that has a lower temperature and less energy. Now, if it was a thermodynamic system, this would have about 10 to the 20 different molecules. So we're dealing with 10 on scales of 10 to the 20, and that's so high that it makes it essentially impossible for us to take energy from this colder region and move it into the hotter region, or to take that improbable state and move it to the more probable state. So really it's not that this process is not possible, it's that it's so improbable that it's essentially impossible on a larger scale. And that's what makes it an irreversible process. Okay, and this comes from the principle of entropy. So I'll just pause so I can write the definition out. Okay, entropy is the thermodynamic variable that describes this. So it says, its symbol is S, and it says, well, it can be interpreted in these two ways. So the probability that a particular macroscopic state will occur spontaneously, or the amount of disorder present in a system. So with this, we can define the second law of thermodynamics. Okay, so the second law of thermodynamics says that the entropy of an isolated system or group of systems never decreases. So this means that the entropy, the degree of disorder, will always increase, or if the system is already at equilibrium, it will remain the same. And so this is why we have heat flowing always from hot to cold. So I have this image drawn up here because you can imagine that the hot molecules in one container and the cold molecules in another, and that's the organized state. And then when you mix them together, they all spread out and we have this more disordered state where it's hot and cold. And so it's not that it's completely impossible for heat to flow from a cold to a hotter substance. It's just that it's so improbable that it is essentially impossible for a system, especially with many molecules. And so this has different applications. And consequences of it are this: heat always flows from hot to cold. Also, we could say that entropy always increases. So the time duration for entropy to increase is in the future. Okay, but let's look at the applications of this for the heat engine and for the refrigerator. Okay, so if you remember, in the refrigerator, what happens is that heat is transferred from this cold reservoir into the system, that's QC, and then work is done so that it can be transferred to the hot reservoir, QH. And so basically we just said, because of the second law of thermodynamics, that there's no way for this to happen without work being done. It will not happen naturally. So that means that we can't have, the limit on this was that COP, the coefficient of performance, cannot go to infinity. So the coefficient of performance for the refrigerator is QC over the work done on the gas. And we can't have that work being zero because that would mean that heat does transfer from cold to hot spontaneously. So we need to have the work done non-zero, so which means that the COP can never reach infinity. And that is a consequence of the second law of thermodynamics. All right, similarly for heat engines, this one isn't as obvious to show, but the efficiency was the work done by the engine over QH. In a perfectly efficient heat engine that we can imagine, we would have all of the heat coming in from the hot reservoir, comes in from the hot reservoir for a heat engine. All of that would go into doing useful work, Weng. We also said that Weng is QH minus QC. So if that was the case, if we had a 1 for our efficiency, QC would be 0, meaning that no energy is discarded. None is lost into the cold reservoir. So to understand why that's not possible, let's consider connecting this imaginary, perfectly ideal heat engine to a normal refrigerator. So one that, not a perfectly efficient refrigerator, just a regular one. So in our heat engine, this is the heat engine. If it was perfectly efficient, we would have QH coming in, and then that's going to transfer out to the work done by the engine. And then that's going to go, put a box around that for the heat engine here. And then that would go over and connect. Let's connect it to a refrigerator. So it connects to the refrigerator, and in the refrigerator, we're going to have QC coming in from the cold reservoir and going out as QH. And that's Wn. So we're using the heat engine to do the work to operate the refrigerator. And this is the refrigerator here. And this is just a regular refrigerator, not perfectly efficient, as I said. Okay, so if you imagine combining these two devices, the net effect from all of this, since this work essentially cancels out, is that we have no external work done on this entire system, and we still end up with heat going from cold to hot. So we know that's not possible. So the net would be heat going from QC to QH. And so since that can't be possible, it's kind of a thought experiment. It tells us, well, we can never have this perfectly efficient heat engine. It's not possible theoretically. Okay, so we know for the heat engine that it cannot have an efficiency of 1, but let's look at how to determine the maximum possible efficiency for a heat engine, which is lower than 1. So it turns out that the maximum efficient, or the most efficient theoretical engine that could be constructed, is called a Carnot engine. And the Carnot cycle is for a perfectly reversible heat engine. So that means that all of the directions of energy transfer could just be changed, and then it would operate as a refrigerator, essentially. So how it works in this Carnot cycle is that, first of all, there has to be any mechanical interactions in the process have to be perfectly frictionless so that no energy is lost. The second most important thing is that in order for this to be reversible, the heat transfer has to occur at the same temperature as the reservoir. Because then if we were to switch the direction here, we would still allow for energy flow in the other direction. So it works just like the heat engine cycle that I showed you before, the Brayton cycle, but just to review, we'll have energy transferred in from a hot reservoir, but this time the gas does have to be at the same temperature as the hot reservoir if it's going to be perfectly reversible. And then it will go through an expansion where it cools to the temperature of the cold reservoir. Again, it has to be at the same temperature as the cold reservoir in order for this to be reversible eventually. And then it goes through a compression to heat it back up to the temperature of the hot reservoir. So in order to see if a heat engine of a different cycle is possible, we can compare to this perfectly reversible Carnot cycle. And the maximum efficiency then is the Carnot efficiency, which is 1 minus Tc over Th. And it can be shown that for any heat engine operating between temperatures Tc and Th, its maximum possible efficiency is the Carnot efficiency. So it can only have an efficiency less than that value. And we could write something similar for a refrigerator. The Carnot COP for a refrigerator would be Tc over Th minus Tc. And it's really all I'll say about that, but this concept of the maximum efficiency, or COP, is important when we're analyzing real refrigerator or real heat engine cycles. Okay, so with that, let's look at the example for this section. Okay, example 20. Consider the following design for a heat engine. Calculate the engine's efficiency. Is such an engine possible? Okay, and I'll draw the diagram on my slide here. So if you have a look, I've drawn the engine cycle. We have QH coming in at 100 joules from a hot reservoir at 100 degrees Celsius or 373 Kelvin. And then that energy is lost to the cold reservoir. 70 joules is lost, and then the cold reservoir is at 0 degrees, 273 Kelvin, and 30 joules goes into the heat engine doing work. So to check if a heat engine is possible, what we need to do is verify the first and the second law of thermodynamics. We can check the first law by checking that the difference in the heat transfer in and out equals the work done. So that's from delta E thermal, the change in thermal energy equaling 0. So we can check that here. We can see it's verified as well just because they're easy numbers this time. But 100 joules minus 70 joules equals 30. Okay, so no problems there. It satisfies the first law. To verify the second law of thermodynamics, we need to check that the maximum efficiency of the engine does not exceed the Carnot efficiency. So let's calculate both. The work done by the engine is 30 joules over QH, which is 100 joules. And that gives me 0.3. Okay, so far okay, but let's check the maximum. 1 minus Tc over Th. So 1 minus 273 Kelvin over 373 Kelvin. And if I calculate that, I only get 0.27. So an engine of this type could only be up to 27% efficient, and this one looks like it would be 30. So this efficiency is based on the transfer for any engine between these two temperatures, Th and Tc. And so we found that this one is not possible. Okay, so let me know if you have any questions about that.